Hello and welcome to this video about the randomized K-server conjecture. My name is Coester and I will talk now about our joint work with Sebastien Bubeck and Yuval Rabani, where we refute this randomized K-server conjecture. So let me start by telling you what the problem is, the K-server problem. So in this problem, we are given a metric space and there are K-servers located in this metric space. So in this little example here, the K-servers are these three fire engines. And then one by one, points in our space will be requested. So there's a fire that breaks out, let's say. And whenever this happens, we have to select one of the servers and send it to the requested location. And once we have moved the server there, then the next point will be requested. And again, the algorithm has to select one of the servers to move to that point. And the cost is defined in this problem as the total distance traveled by all the servers. So the goal is to serve all the requests while moving as little as possible. And this is an online problem in the sense that we have to decide which server to send to the current request before we find out the locations of future requests. And as usual in the area of online algorithms, the quality measure of algorithms is the competitive ratio. So we say that an algorithm is row competitive, or also that it has competitive ratio row, if the cost of this online algorithm is at most a row factor larger than the cost of the optimal offline algorithm. So within a factor row of the optimal solution that we could have found if we had known the entire sequence of requests in advance. Within a factor row, and we do allow an additive term here though, so plus some constant, which can be anything that does not depend on the sequence of requests. And the K-server problem has also often been called the holy grail problem of competitive analysis. Specifically, there are two major conjectures related to this problem, which I will tell you about now. One is the deterministic K-server conjecture, or usually simply called the K-server conjecture. So this is the statement that there exists a deterministic algorithm whose competitive ratio is K. This conjecture is almost resolved up to a factor of 2. So it is known that on every metric space with at least k plus 1 points, because if there are at most k points, then the problem is trivial. But if there are at least k plus 1 points, then the competitive ratio is at least k. And there is also an algorithm for general metric spaces whose competitive ratio is known to be at most 2k minus 1. And there are many special cases, actually, where it is known that the competitive ratio of deterministic algorithms is exactly k. So the conjecture here is that it is exactly on k on all metric spaces. Now, the randomized K-server conjecture is about randomized algorithms for this problem and says that there exists a randomized algorithm whose competitive ratio is of order log k, so exponentially better. What is the state of the art about the randomized K-server conjecture? Well, on the one hand, it is known that on every metric space, the competitive ratio is at least log k over log k. Moreover, there are upper bounds for this problem, which are polylogarithmic in k and one additional parameter. So either in k and the number of points in the metric space, or in k and the aspect ratio of the metric space. But on general metric spaces where the number of points and the aspect ratio could be infinite, the best upper bound is actually the one from the deterministic algorithm. Still, it has been conjectured that the randomized competitive ratio is log k on every metric space. And again, there are special cases where it is known that there is a lower and upper bound of log k. Okay, so I'm talking now about this randomized K-server conjecture. So here is the statement again, that there exists a log k competitive randomized algorithm. And what we prove is roughly this statement, except that we have to insert a no into the sentence. So we show that there's no log k competitive randomized algorithm, so thereby we are refuting this conjecture. More precisely, what we show is that there exists some metric space of k plus 1 points where the competitive ratio is at least log square k. And we also consider this universal lower bound, so we also show that on every metric space of at least k plus 1 points, the competitive ratio is at least log k. So this second result is improving over this log k over log k lower bound that I mentioned on the previous slide, which holds on every metric space. And the first result, well, the middle theorem here says that there are some metric spaces where the competitive ratio is at least log square k. And this middle result here, this is what is refuting the randomized K-server conjecture, saying that it is log k on all the metric spaces. Okay. So how do we prove this? Well, for the proof, it will actually be more convenient to talk about metrical task systems. And in fact, we will also improve and tighten the lower bounds for metrical task systems. So metrical task systems, MTS, is another central problem in online algorithms and one of the most general problems you can possibly define. So here we are also given a metric space, and this metric space has exactly n points. And now there is one server in this metric space, and it's initially located at some point, let's say P0 in this metric space. Now at every time step, so at t equals 1, 2, and so on, a cost function arrives. This cost function, this maps every point of the metric space to some non-negative number, possibly infinite. Now after this cost function is revealed, the algorithm has to choose a point in the metric space, so it can move to some new point pt with its server. And then the algorithm has to pay a movement cost, which is just the distance in the metric space between the old location and the new location. And it also has to pay the service cost at this new location. Now, one thing that is known is that this MTS problem, in the special case where every cost function only takes value 0 or infinite, is equivalent to the n-1 server problem on this same metric space. So when the number of servers is 1 less than the number of points in the metric space. The reason why this is true is, well, if you think of the K-server problem in a metric space that has exactly 1 more point than the number of servers, that means that at all times there's exactly 1 point that isn't covered by a server. And this hole that doesn't have a server corresponds to the one server in metrical task systems. And if we want to model a K-server request at some point R in the metric space for K-server, to model this as a metrical task systems, it is like giving cost function that places cost infinite at this one point and cost 0 everywhere else. And that is therefore forcing the whole, the point that doesn't have a server, to be anywhere except at the one requested point. So therefore, these two problems are equivalent in that sense when we have a metric space of exactly 1 more points than the number of servers. And what this means is that our lower bounds therefore also give improved lower bounds for metrical task systems. So there is a lower bound of log square n on some metric spaces of n points for metrical task systems, which is tight because we know that on every metric space there's an algorithm which is log square n competitive. And we also have a universal lower bound of log n on all the metric spaces. And this is also tight because it is known that on some metric spaces there is an algorithm whose competitive ratio is at most log n. Okay, so how do we prove this? Well, first of all, let me tell you what the previous lower bound of log n looked like. So this was shown already in the paper that first introduced metrical task systems by Borodin, Lineal, and Sachs in 1987. So this lower bound of log n is very simple. So we have a metric space where all the distances are the same, the uniform metric, or you can think of it as a star. So the points of the metric space are all these leaves of this star. The distance between any 2 points is 1. Now, the cost functions are of the following form. At every time t, the cost is infinite at a single point rt, and the cost is 0 at all the other points. And this point rt is a point that is chosen uniformly at random among the leaves of this star. Okay. And so that means if the cost infinite comes at the location where the MTS algorithm has its server, then it has to move to some other location. And then in the next time step, cost infinite will come somewhere else, and it keeps going like this for a long time. So whenever the algorithm gets hit with this infinite cost, it has to move to some other point. Okay, so what is the cost of the online algorithm in this setting? Well, at every time step, because we choose this point uniformly at random, it means there's a 1/n probability that the online algorithm will have to move to some other point for cost 1. So therefore, the expected online cost is the number of requests divided by n. Moreover, the requested offline cost, well, I claim that it's the number of requests divided by n log n, and this follows from a coupon collector argument. So specifically, if the online algorithm, if the offline algorithm gets hit with this infinite cost, it has to move also to some other point. But because it's the offline algorithm, it knows what the best point to move to will be. So that algorithm would then move to the point whose next time that it gets infinite cost will be furthest in the future. And now by a coupon collector argument, it takes in expectation n log n steps until all the points get infinite cost, and therefore the offline optimal algorithm only has to move once every n log n steps in expectation. And now the ratio between these two quantities is just the lower bound of log n. Okay, so how can we now improve upon this lower bound of log n that has been the best lower bound for the last 35 years? So here's some intuition. It comes from this poem. So it turns out that actually this lower bound was apparently known already more than 100 years ago. So how does it work? Well, the metric space will have two paths that diverge in a yellow world in two directions. And now our online algorithm will have to move along one of these two paths. It cannot travel both. So it will start going down one of them and then maybe the other one, because it might look like it's a better one. But actually, it turns out they are about the same. And it proceeds like this, and it's quite unclear which of the two paths will be the better one, the one with less movement. So the online algorithm will be in doubt of whether it should switch to the other one, come back, or just proceed on the path that it's on. In contrast, the offline algorithm knows what the request sequence will look like, and that algorithm will take the path less traveled by, and that is what will make all the difference in this lower bound. And that is essentially the whole proof. I will get into a bit more detail in a moment. First, let me tell you what the metric space really looks like. So it's very similar to the diamond graph, which is a known metric space or class of graphs that has been used for other purposes before. So what is a diamond graph? It's a recursively defined class of graphs. So the base case, M1, is just well, 4 vertices arranged in a circle. And now to construct MW plus 1, you take one copy of the previous MW, well, you take 4 copies of MW, and then you arrange them together in a circle like this. And so therefore, this is what the first 3 diamond graphs look like. And these two paths that diverge in a yellow wood are essentially the top path here is one of them, and the bottom one is the other one. Now, the only thing that's different in our metric space is that it's a bit simpler to show the proof. If we take not 4 but 6 copies of the recursive metric space, so the way the family of metric spaces looks like then is this. So at the very left of my screen, I have a tiny circle of 6 points. Now, if you take 6 copies of those, glue them together, then it looks like this. Take 6 copies of those, glue them together, 6 copies of this, and so on. So this is the family of metric spaces, for which we will show that the lower bound is at least log square n. Okay. Now, let me get into some more mathematical detail of how to actually do this. I will show now a lower bound of log n over log n squared. So this is slightly weaker than the lower bound I claimed before of log square n, but it's simple enough that I can essentially explain it almost fully in the next couple of minutes. Okay. So we want to construct a metric space recursively, and we will always denote this metric space by this MW. And now what we want to do recursively is that we construct also a request sequence in this metric space. And the well, recall that I'm taking this view of metrical task systems. So there's a single server instead of k servers. And I can give this 0 and infinite cost at locations. And whenever I give infinite cost somewhere, the server has to move somewhere else. Now the request sequence will be such that it forces the server, which is starting at this leftmost point, to slowly move through this metric space to the rightmost point. So I have infinite cost everywhere, except that at some points under this white bar, there will be points that have 0 cost. And therefore, the online algorithm and the offline algorithm as well has to follow this white bar. And the properties that we're going to show is that the optimal offline cost is equal to the diameter of this metric space. So the diameter will, in this case, just be the distance from the leftmost point to the rightmost point of this metric space. Whereas the cost of the online algorithm will be at least, and yeah, RW is a quantity that we will have to find. This will be our lower bound on the competitive ratio. So the online cost will be at least RW times the diameter of this metric space. Okay, so if we show these two inequalities, or this equation and this inequality, then this will mean that there is a lower bound of RW on the competitive ratio of any online algorithm. Okay, so let us do the construction and determine what RW is. So instead of just taking 6 copies, as I said before, this is the simpler lower bound where I'm losing some log-log factors. So the construction now looks a bit different. I will take 3 times RW many copies on, well, in fact, 6 times RW many copies of our recursive metric space, and I arrange them like this, that I have a path of 3 RW copies at the bottom and a path of 3 RW copies at the top, where RW is the competitive ratio that we have proved by induction for the previous step. By the way, the base case of this induction is you can just take a path and then you give a cost function that is 0 only at one point and infinite everywhere else, and this 0 point slowly moves from left to right on this path. And that will have these 2 properties where RW is 1. Okay, so base case of induction is not a problem. So now in this inductive case, so I'm constructing this metric space by taking these many copies of MW and arrange them in this way to obtain my space MW plus 1. Now, what is the request sequence? Well, we want the request sequence to be such that the server starts here, and it will then be forced in some way that we will have to describe to end at this rightmost point. Okay, how do we do this? Well, the request sequence consists of 3 phases. And the first phase will be played on these first RW copies at the bottom and top, and then the second request sequence on this middle segment of RW copies at the bottom and top, and in the last stage of the request sequence, we will then eventually force the algorithm to reach the right end. Okay, so in the first phase, we're not doing anything particularly intelligent. We are just giving the recursive request sequence on the bottom and the top branch at the same time. So all that this is doing is that it's forcing the online algorithm to move forward on one of those 2 branches and reach either this point at the top or this point at the bottom. So the cost of this first phase it is, well, RW, because we will advance through RW copies. And then in each copy, the online algorithm has to pay by the induction hypothesis at least RW times the diameter. So the cost of the online algorithm so far is RW square times the diameter of these individual copies. Now in the second phase, we will repeatedly do the following. We will flip a coin. Now, depending on the outcome of the coin, we will issue the recursive request sequence in either the next copy on the top path or the next copy on the bottom path. So let's say that the outcome here is that we advance the request sequence on the bottom path, but simultaneously in all of these requests, we still give a cost of 0 at this one point here on the top path. So that means that if the online algorithm, or in fact the offline algorithm, if that algorithm is at this point, then it doesn't have to pay anything for this step because it can just stay at this point. But if it's at the other point, well, then it has to pay the cost of the recursive sequence in order to advance one copy further. And then we flip a coin again and repeat this several times. So of course, the algorithm could decide to switch to the other path when the top path here proceeds by one more copy. The algorithm could say, okay, well, I don't want to advance. Let me switch to the other path instead, where this one is not advancing. But the point of this first stage was to create a large enough distance here so that this would be expensive. So in other words, if the algorithm switches from one branch to the other branch, the cost is even larger than just accepting to play this inductive sequence. So we can kind of ignore this case. And now we do these coin flips for RW times. Okay. So each time there's a probability of 1/2 that the online algorithm will have to advance on the side where it's on. So there are in expectation RW over 2 copies for which the online algorithm has to pay the recursive cost, and the recursive cost, as before, is RW times the diameter. So the cost of this second stage is therefore 1/2 of RW squared times the diameter of the individual copies. And now the observation is that because in each step we flip the coin to decide where we advance, these two branches will not be exactly equally advanced in expectation. So one of the two branches will tend to be more advanced than the other one. And specifically, the gap between the more and the less advanced path will be of order square root of the RW, because RW is the number of times that we flip the coin. Now, this is what we're going to take advantage of. So let's say that the bottom path is less advanced than the top path. Now we give cost infinite also at this point on the top path. So this is killing this path and forcing any algorithm now to be at this bottom path. And now in the last stage, we continue calling the recursive request sequence only on this less advanced path until we force the algorithm to reach the right end. Okay, so in this last stage, the number of copies that the algorithm has to advance is, well, it's RW here. And before that, it's RW over 2 plus square root RW from this middle segment. So in total, there are 1.5 RW plus square root RW copies to be traversed in this last part of the request sequence. And again, in each time, the cost is RW times the diameter. Okay, and if we add all of these costs up, then you can calculate that the total expected cost of the online algorithm is 3 times RW plus square root RW times RW times the diameter of the individual copies. Now, in contrast, the offline algorithm can serve the entire request sequence only for cost 3 times RW times the diameter. The reason is that, well, the offline algorithm knows in advance which of the two paths will end up being more advanced and therefore which of them will be killed. So the offline algorithm will just choose the path that will not get killed and move along the shortest path from the left end to the right end as the request sequence gets revealed. We know that in each copy, the offline cost is just the diameter of the copy. So therefore, it can move from the left end to the right end for 3 RW, because this is the number of copies it has to go through, times the diameter of these copies. Now we want to calculate what is therefore the lower bound on the competitive ratio in this MW plus 1. Well, so for this, we just need to take the ratio between these two quantities. So RW plus 1, our new lower bound, can be any number which is at most this ratio. So we can just choose it to be, if you calculate it, you get that RW plus 1 can be at most RW plus square root RW over 3. And a solution to this inequality is, for example, to define RW to be W squared divided by 81. And well, I did cheat a little bit here because actually this square root RW has another constant factor here that is involved. The point is, at the end you do get only something that is quadratic in W up to a constant factor. So W square is our lower bound. But now what is that as a function of n, as a function of the number of points in the metric space? Well, let's see how many points are there. Well, the number of points in the metric space is 6 RW times the number of points in the recursive metric space that we have used before. And now we can just use induction and therefore obtain this sum of 6 Ri. Now, if we plug in the equation for Ri that we had here, W squared over 81, then you can replace this by the product of these I squares. So this just ends up being W factorial square, which is exponential in W log W. Okay, so our lower bound, which is W square, if we express it as a function of n, then it would be log n over log n squared, because W, if you rearrange this for W, then W is of order log n over log n. Okay, so and this is essentially the entire lower bound of log n over log n squared, which already is good enough to refute the randomized K-server conjecture. Let me tell you briefly how to remove the log. So the idea is that instead of using 6 RW copies, we only use 6 of the recursive metric space. So this will have the effect that the number of points in our metric space then is only 6 to the W, and therefore our lower bound of W square will become log square n. Now, technically, this leads to some complications because we cannot issue the recursive request sequence all at once. So the idea that we use here is that we issue the recursive request sequence only chunk by chunk. So we don't invoke the entire induction hypothesis in a sense, but only a little piece of it, so that we can slowly advance on the two branches. And technically this then becomes a bit more tricky. And we also don't flip fair coins, but an unfair biased coin in this second stage, and need the martingale version of the central limit theorem, or the Bayesian version of it, to conduct the analysis. Okay, but this is all the detail I want to give about this for now. So if you have some lower bound that is recursive and that you think you could improve a bit, then I encourage you to look into our paper and see if an idea like this recursive chunk by chunk could work in that case as well. In fact, we did use this same idea now as well to tighten the universal lower bound for the problem, which, as I mentioned before, previously was log k over log k. We improved it to log k. So on every metric space, the competitive ratio can be no better than log k. Now, these lower bounds also have some implications for other problems. So the k-taxi problem, the distributed paging problem, and metric allocation, all of these are generalizations of the k-server problem or metrical task systems. So therefore, they directly inherit the new improved lower bounds that we have shown. And moreover, for the layered graph traversal problem, we slightly modify our construction that I just explained to you, which for this problem then gives a lower bound of omega k square, which also is exactly tied up to a constant factor because of a recent upper bound that we have shown in a different paper last year. Okay, so let me conclude. So the competitive ratio of metrical task systems is log n on the easiest metric spaces, and it's log square n on the hardest metric spaces. So this is therefore resolved up to a constant factor. And in particular, this log square n, the upper bound is based on algorithms that use HST embeddings. So surprisingly, this technique of HST embeddings is the best you can do for this problem in general. And for randomized k-server, we now have tight bounds on the easiest metric spaces of log k and on the hardest metric spaces of k+1 points of log square k. But in general, if you allow more than k+1 points, there's still a large gap here between the lower and upper bounds. So as I mentioned earlier, the upper bounds that are polylogarithmic also depend on either the number of points or the aspect ratio of the metric space. If you only want dependence on k, then we don't know anything better than the deterministic algorithm that is 2k-1 competitive. So there's still a very interesting gap here. Now, to finish, let me leave you with these takeaways printed at the bottom of the slide. So yeah, in particular, I want to tell you to never underestimate the power of poems if you are stuck trying to find a proof for something.